How's it going, ladies and gentlemen? Mr. Donahue here once again. This time we're going to take a look at radioactivity. So our objectives will be to describe the discovery and detection of radioactivity, describe the nature, penetration power, mass, and charge of radioactive decay particles, including beta, positron, gamma, and alpha particles, and why are some isotopes stable and others are not. So let's take a look. So the discovery of radioactivity was by Henry Becquerel, and he was studying fluorescence and X-rays. Basically, fluorescence is if I had this substance here, a certain wavelength of light comes in, it excites this material, and then that material emits a different color wavelength, and that's fluorescence. It's kind of like if you've ever seen a highlighter under a black light, it's fluorescing. So he was studying that, and he had some rocks that he thought fluoresced X-rays from being excited by sunlight. So he was exposing exposing photographic film to the rock that was being exposed to the sun. But then one day, it was cloudy, so he never took the film out of his drawer, and he left the rocks on top of them, and he decided to develop that film anyway, and he noticed that, hey, would you look at that? It exposed the photographic paper, even though the rock was never exposed to any sunlight, so it couldn't have been fluorescence. Couldn't have been fluorescence, and where's that, stuff coming from? So taking a look at what kind of particles are being emitted, we could set up this little experiment. We have this little containment vessel that's going to stop any radioactivity from going in those directions. So we have a particle stream coming straight out, and we have two different charges. We got a positive charge over here, we have a negative charge over here, just a magnetic field, and we have some sort of detection apparatus like film paper for the particles to travel towards. We noticed that some of the particles were bent towards the positive magnetic pole, which means it's a negative charged particle. We saw particles were attracted to the negatively charged pole, which tells us that they were positively charged, and we saw some that went straight, so there is no charge on those particles. So we know we have at least three different kinds of particles: one positively charged, one negatively charged, and one with no charge. So let's talk about all the possible radioactive emissions. So we got alpha particles, which is basically has a mass of 4, charge of 2. It's basically a helium nucleus without any of the electrons. So we also can see the notation like this. We see an alpha symbol and then 4 and 2. We could have beta particles, which are kind of like electrons, but they're coming out of the nucleus. And the notation we use for that is either this a beta symbol with a minus sign, or you can give the notation -1 for its charge, 0 for its mass, and an E for its symbol. We also have gamma emissions, which we give a little gamma symbol. It looks like a fancy, weird-looking Y. We also have positron emissions, which looks a lot like the beta particle notation, but it has a positive charge. It's also written as an electron, kind of, but with a +1 charge. It's antimatter. It's actually the opposite of an electron. If a positron and a beta particle come together, they annihilate and release a bunch of energy. And then we have neutrons, which have a charge of 0 but a mass of 1, and notation for that is this little n for neutron. All right, so let's talk about penetrating power. So different emissions have like different levels of threat, and they can penetrate materials to a certain extent. Alpha particles are the weakest as far as penetration power goes. You can stop alpha particles with just some paper. So if you got a little paper, you put it around your radioactive stuff, it stops all the alpha particles. It's even stopped by a few feet of air. So if you're like just far away from the alpha source, you don't got to worry about alpha particles. Whereas beta particles, they need some foil. All right, this material, foil, is more dense. There's more matter in the way, so you need some foil to stop some beta particles. And gamma radiation is the one with the highest penetration power. You need a lot of material, a lot of mass in the way of the gamma material to stop it. So usually you look for things like lead or tungsten, something that's very, very dense, or a bunch of water to stop all of that gamma radiation. So gamma has the strongest penetration power. Well, why are some isotopes radioactive and others aren't, you may ask? If I have carbon-12, well, it's got 6 protons, that's why it's carbon, and for a mass of 12, it's got 6 neutrons, whereas carbon-14 still has to have 6 protons because it's carbon, but this one has 8 neutrons. So why is carbon-14 radioactive, but carbon-12 isn't? So it has to do with nuclear stability. We're basically just describing how stable the nucleus is. So if we have a stable nuclei, then it's not radioactive. But unstable nuclei, they are radioactive. They're going to give off particles because they're unstable. Well, why are some of them stable and others aren't? Well, there's a bunch of different reasons. One, it might be too big. The nucleus might be too big and it's got to get smaller, so it's going to be looking to give off a bunch of particles. There may be too many neutrons. So if you take a look at carbon-14, you can see they have more neutrons than carbon-12 does. Or they might not have enough neutrons. Maybe there's not enough neutrons, and that's why the nucleus is unstable. Or sometimes, if the nucleus just has too much energy, if that nucleus is too energized, then it will be radioactive. And if we take a look, here's the belt of stability. So on the bottom, we have the atomic number, and on the left, we have the number of neutrons. And you can see for smaller atoms, the dark red is stable. And for smaller atoms, you can see it's almost a 1-to-1 ratio of neutrons to protons for where they're stable. Then after that, you can see most of the stable stuff is a slightly different ratio. It's almost 1.5 neutrons for every proton. So we're looking for something close to that to make it stable. And then after atomic number 82, everything is unstable. You can see right here is the last stable isotope. Anything greater than that is too big. And those isotopes are all going to be radioactive because they're too big. So anything after lead, number 82, is going to be radioactive because the nucleus is too big. So to summarize, can you describe the discovery and detection of radioactivity? Can you describe the nature and penetrating power, mass, and charge of radioactive decay particles, including beta, positron, gamma, and alpha particles? And why are some isotopes stable and others are not? All right, I hope you found that helpful and see you in class. Okay, bye.